work we were doing in the last video on Aufbau's principle and writing electron configurations. So you sent me the electron configurations that I asked you for, and you all seem to be fine. Just be careful that you're filling the 4s sub-level before the 3d, okay? So remember that. So Aufbau's principle states that when building up electron configurations of atoms in the ground state, the electrons occupy the lowest available energy levels. So you have to fill 4s first because it's lower energy than 3d. Now, there are two exceptions to Aufbau's principle that you need to know about. They're chromium and copper. So the minute you see chromium and copper written in an exam question, you're thinking, hang on now, these are the exceptions to Aufbau's principle. Chromium has 24 electrons, okay? So when I start writing it, I'm just going to fill the electrons in the lowest available energy levels. Then you're putting in 1s2, 2s2, then it's 2p6, 3s2, 3p6, 4s, remember now, has lower energy. Just get rid of that there. 4s has lower energy, so it's 4s2. And now, how many electrons would I be putting into the 3d sub-level? So count them up. 2 and 2 is 4, and 6 is 10, 12, 18, 20. So it's 20 in already now, so I need to put 4 in, okay? That's according to Aufbau's principle. Now, what happens actually is that one electron flips over from the 4s sub-level and goes to the 3d sub-level. So what you actually end up with is that. So you'd write the rest of it, you know, when you're doing it. So 1s2, 2, and so on. Now, why does that happen? Well, what you have now is you have a situation where the atom has two half-full sub-levels, okay? Remember, you can put 2 electrons into the 4s sub-level, so 4s1 is half full. You can put 10 electrons into the 3d sub-level, so 3d5 is half full. The fact that the atoms now have two half-full sub-levels makes the atom more stable, and so it takes that arrangement. So this is what you'd have to write if you were asked for chromium's electron configuration. It's an exception to Aufbau's principle. Now, copper has 29 electrons. So if I was to write copper's electron configuration using Aufbau's principle or following Aufbau's principle, 4s2 would bring me up to 20. So then I'd be writing 3d9 there. But what actually happens then again, look, is that one electron from the 4s flips over to the 3d. So you actually end up with 4s1, 3d10. The fact that that 3d sub-level is full means that the atom of copper is more stable, and so the electrons go that way naturally, okay? So there are the two exceptions. So be mindful about the two exceptions to Aufbau's principle. Now, the last part of this chapter then talks about sub-levels and how we have to know the difference, I suppose, between sub-levels and orbitals. So do you remember the diagram the last day? So you started off with your 1s, and then you have the second main energy level is divided up into 2s and 2p. The third main energy level then is divided up into 3s, 3p and 3d. And remember we said that the 4s sub-level has lower energy, so that fills in there below the 2, 3, 4, 5, below the 3d. So now, just be careful about the terms. So sub-level is a subdivision of a main energy level, okay? So this is now there isn't any subdivision for the first main energy level for n equals 1. This is n equals 2 subdivided into 2s and 2p. Here you have n equals 3 subdivided into 3s, 3p and 3d. So sub-levels are subdivisions of energy levels. Now, they consist of one or maybe more orbitals. So now we're meeting a new term that I on purpose didn't meet or didn't mention the last time. So we're meeting orbitals now. Now, an orbital is a region in space where there's a high probability, 95%, of finding an electron. Now, you need to look at each sub-level now. So the S sub-level here is actually just made up of one orbital. So that's just one orbital, okay? And it's just called the S orbital, all right? The two S sub-level, again, it's the S sub-level, look, so just one orbital, and the 3s sub-level, one orbital. So the S sub-levels consist of just one orbital, okay? The P sub-levels, though, see the way they're broken into 3, look, 2, 3. So the P sub-level is actually made up of 3 orbitals, and you need to know the name px, py, and pz. So px, py, and pz. And the D sub-level is actually made up of 1, 2, 3, 4, 5 orbitals. Now, I'm just going to rewrite that there now again to make it really clear. So the S sub-level consists of one orbital. That's why it's drawn in a straight line. The P sub-level is made up of 3 orbitals, and you need the names as well. Px, Py, and Pz. And the D sub-level is made up of 5 orbitals, and you don't need the names of those. Now, the other important thing to remember is that each orbital can hold 2 electrons. Okay? Now, 2 last definitions that we need to run through. Hund's rule of maximum multiplicity. Now, if you heard of a multi-story car park or multiple berths or something like that, you'd be thinking more than one, wouldn't you? So multiple implies more than one. So Hund's rule of maximum multiplicity states that when 2 or more orbitals of equal energy are available, then the electrons have to occupy them singly, and then and then they come back and fill them in pairs. Now, the second definition that I'm just going to mention firstly, and then I'll explain it a bit better, is Pauli's exclusion principle. Now, Pauli's exclusion, if you're excluded from school, you're not allowed in. So Pauli's exclusion principle, excluding no more than 2. So 2 are allowed in, and that's it. No more than 2 electrons can occupy an orbital, and they have to have opposite spin. Now, I'm going to use both those definitions there now and draw what are called electron in box diagrams, just in case you're asked to draw one. Now, I'm actually going to start with boron, and then I'm going to draw carbon, nitrogen, oxygen, and you'll get the idea of what I'm doing then. Now, I'm drawing an orbital as a box, okay? So that actually, one second now, I'm just going to rub out this one. Oopsie. I'm just going to rub out that one there because that's too big. So I'm just going to draw, this is my 1s orbital, okay? This is my 2s orbital. This is my 2p orbital, and I'm just going to make that into, I have to divide that up into 3, you see, because you have px, py, and pz, okay? Now, boron has 5 electrons. So when you use Aufbau's principle and you put the electrons into the boxes. So 1s2, 2s2, and 2px. And you're just putting in 1 there because that's your 5 electrons. So the arrows are the electrons, okay? And the boxes are the orbitals, okay? So now, carbon now has 6 electrons, right? So when I'm going to put it in, I'm going to fill the 1s first. I'm going to fill the 2s. Now, what did Hund's rule of maximum multiplicity say? I now have 3 orbitals of equal energy available. I had to fill these first because they had lower energy. But these 3 orbitals now have equal energy available. So what does Hund say to do? The electrons have to occupy them singly first and then come back and fill them in pairs. So this will become a bit clearer now in a second, okay? So now I'm going to draw nitrogen. Nitrogen has 7 electrons. So again, I'm going to fill my 1s2, 2s2. I have to fill them first because they are lower energy levels or lower sub-levels, so I have to fill them. Now I'm coming to the next sub-level, which is the 2p, and it's showing me here that I have 3 orbitals of equal energy available. So what does Hund say to do? Have to fill them singly first, and then I'm going to come back and fill them in pairs. Now, the Pauli's exclusion principle was that no more than 2 electrons can occupy an orbital. I'm only putting 2 arrows into each orbital there. And do you notice that I'm drawing 1 up, 1 down? Because they have to have opposite spin. Now, just finally here, okay, you'll see what's going on here now with oxygen. Oxygen, I have to fill the 1s first. I have to fill 2s then because it's lower energy and I'm following Aufbau's principle. Now I'm getting to a situation where I'm meeting 2px, 2py, and 2pz. They have equal energy. What does Hund say to do? Fill the electrons singly first and now come back and fill them in pairs. Okay, after oxygen, then you've got fluorine with 9. I'll just quickly draw fluorine there then as well, and you'll see what I'm getting. So 1 up, 1 down. So you're filling 1s first, then you're filling 2s. Now look, you're coming to a situation where the 2p sub-level is divided up into 3 different orbitals, but they have equal energy. So you fill them singly first, and then you come back and fill them in pairs. Okay, thank you.